football weekend, Ohio State won. US M1, so everyone's happy. A couple announcements. We have a lecture quiz that will open today at noon, as will your exam 1. Both of those are due tomorrow at 12. So your lecture quizzes, again, are 6 points. Your exams are 30 questions. There were 2 points apiece. So that's how we differentiate sort of the weights between the assessments. So total for Module 1, you have 48 points for your quizzes and 60 for your exams. So right now we have a total of 108 points. Those are the required points. And then you have 2 bonuses. Subscribing to the YouTube channel to get screencasts as they're posted. And then that practice exam 1 was worth 30 points. So your required plus your bonus divided by 108, that gives you 40%. And then you can go into the syllabus and see where you fall in terms of the letter grade. That's essentially how I calculate your grades. As we add more points, the bonus never adds to the bottom number. So the bottom number is always your required points. The bonus is just meant to pep up your numerator. And what else is up there? So you can do that. I think interim grades are due sometime in October, and whatever date they're due, I'll basically look at the required number of points at that time, stick in your earned points, which is equal to the required plus the bonus, and that's how I calculate your letter grade for the interim. Any questions before we get started? Yes.
So is this ever going to work with the practice exam? We can start and stop it during the time frame, or does it have like a time limit?
There's no set time limit once you open it, but you have 24 hours to do it. So again, I haven't opened the browser and let it sit for that long, so I don't know if it kicks you off or what happens. If you do experience some issue, shoot me an email. I'll have to do a reasonable time tonight. I have kids, so I'm out at about 8. So don't expect any replies after that. I'll check my email again tomorrow morning around 8 a.m. But make sure you do your best to set aside some time to get that done. Again, if you miss the exam, those 60 points will be tacked on to your final. But again, just make sure you try to do it. It shouldn't take you more than 45 minutes, 60 minutes to do it. If you did that practice, it looks just like that. The 2-column format, choices A, B, C, and D. Yep.
Are there questions about the same level of difficulty, or is it?
We're gonna Emerald Lagasse and kick it up a notch, so they're a little spicier. They're not terribly difficult. Everything goes back to these slides, so you should be able to find an example that we did as you go through it. So the other thing, there's no lockdown browsers. I'm not watching anything. The only thing I see is when you basically submit it. So don't forget to, if you take it, remember to submit it at the end. I don't see any sort of movement of how you're looking in the web browser or anything. All I see is your submission time. So today we're going to do two main things, calculate formal charge. And again, that's when an element is not in the neutral bonding pattern. We saw some cases where the element had a charge. And then we're going to talk about resonance. So resonance is the movement of electrons or these other things called radicals, which are single electrons, or essentially no electrons, which is a plus charge. I thought we would start off by sort of going through two examples of this, taking a molecular formula and making constitutional isomers, so that you get practice in drawing the functional groups and just identifying the bonding patterns of the functional group. The compound names we will not talk about until probably module 3 when we get into nomenclature. So the formal name of the compound we're not worried about, just what functional group is there. So I like these problems a lot, again, because you can use your imagination. You're basically taking the given molecular formula, finding degrees of unsaturation, and then just building. So you're taking the C4H10O, all of those atoms, in building molecules with the functional groups under the constraint that they have to be neutral and obey the degrees of unsaturation. So let's start with CnH2n plus 2. And we have 4 carbons. So N equals 4. And so for 4 carbons, the maximum number of hydrogens should be 10. So we're just plugging that into the 2n plus 2. And we find that in the molecular formula we're given, last time we talked about the influence of heteroatoms, and oxygen doesn't add or subtract. So we'll say theory, and then given. And so basically we get H0, so there's no degrees of unsaturation. So let's just start drawing some constitutional isomers now that have an oxygen in it. So there's 4 carbons. So if we wanted to make an alcohol, we could put the OH group at carbon 1. And so we would say alcohol. Maybe I'll write that here. We could draw a constitutional isomer of that where we put the hydroxyl group at carbon 2. So for the longest linear chain being 4 carbons, I think that's probably the only 2 constitutional isomers we could draw. If we went down in carbon count to 3, so now we would have to put a methyl group, so a single carbon and a hydroxyl group in there. The methyl group can't go at 1 or 3, so we have to put it at 2. And now we have the hydroxyl group, so we can put that at basically, we'll start at position 1. And then we could draw a 4th alcohol isomer. Where it's now at position 2. And so in blue, we learned how to classify alcohols. So this would be a primary alcohol. This would be secondary, primary, and then the last one would be tertiary. I'll leave it to you to go through those and determine the uniqueness sets of the carbons and hydrogens and the ratios. So there's no degrees of unsaturation. What was the other alcohol or the other oxygen functional group named that had no degrees of unsaturation in it? So an ether, so we can draw some ethers. Now remember, an ether, the oxygen is bonded to 2 carbons. So there's 2 carbons in I'm going to put basically, instead of that second carbon, I'm going to make it an oxygen. So now I have 1 carbon. I need 3 more, or yeah, 1 carbon, the oxygen. Now I need the 3 other carbons. So that would be an ether. I could also put the oxygen, draw 2 carbons, then the oxygen. So that's another ether. Then I think I can draw 1 more. So those would be 3 ethers. Yeah. So, like, put it right here.
Yeah.
So if we did that, this compound is the same as that one. So if you can imagine taking either one of them and just like flipping it 180 degrees, they map onto each other exactly. So one of the things you'll see over the course of the semester, as we get into Module 3, particularly the way things are drawn, as long as they have the same connectivity, they're still going to be the same isomer. You can do these flips in rotations and things and still draw the same thing. So maybe 2 words to describe ethers. So we would say that one is symmetric because both of the groups bonded to the oxygen are the same. And then the other 3 are non-symmetric. And when we talk about symmetry, it's really sort of a mirror plane. Yeah. Right here?
No, on the alcohols. The 3-carbon alcohol with the methyl group coming out of the 2. Does that not be a 4th carbon on top?
This one?
Yeah.
So you have 1, 2, 3 carbons, and there's your 4th one.
So there are 4 carbons.
Yeah.
Okay.
So this carbon number 2 does not have any hydrogens attached to it. One thing I want to point out while we're talking about it, if you see something like this, so in these 2 cases, that line coming off, keep in mind that's a carbon. Heteroatoms explicitly have to show their number of hydrogens. So the OH is always showing that H. This bond here, that's to a carbon. So 1 carbon, that's bonded to 3 hydrogens. if there's like oxygen, and then as we'll see a little bit later for formal charge, if it doesn't obey that sort of 2 bond, then it most likely has a charge associated with it. So let's move on now. What we're basically going to do is take C4H8O. So we're going to knock off 2 hydrogens. That's going to give us a degree of unsaturation. And you'll see that for that, we can draw a lot more constitutional isomers that have different functional groups. So we're always using that CnH2n plus 2. So we know that for 4 carbons, we should have 10 hydrogens. In the molecular formula, oxygen doesn't alter the given hydrogen count. So that's going to stay as C4H8. And a degree of unsaturation is defined as H2. So that's going to give us 1 degree of unsaturation. We could probably spend the rest of the lecture just drawing constitutional isomers for this one. There's probably 30 or 40 or more. There's quite a bit. And the reason there is, remember that a degree of unsaturation can be a pi bond or a ring. Now think of the types of pi bonds that we learned. We have carbon-carbon, so that's the alkene. We have carbon-oxygen, that's the carbonyl. So I'll draw maybe like 4 maximum, so two sort of each, 2 with a pi bond, 2 with a ring. So the best thing to do is just start with 4 carbons. Now, if we wanted to make the degree of unsaturation an alkene, we could just put the double bond between 1 and 2. But we still have that oxygen to contend with. So we can stick that on carbon 1. But then you could move that OH group to carbon 2, to carbon 3, to carbon 4. And those are different constitutional isomers. What if you wanted to make the degree of unsaturation a carbonyl? You could put the carbonyl group at position 1. So that would make an aldehyde. You could move it over to position 2. That would make a ketone. So just to point out, if you were to draw this, so that compound is the same as the first one. Now, if we're using the degree of unsaturation as a ring, there's no pi bonds in these constitutional isomers. So we could do 4 carbons and then the oxygen in the ring, so that would be 5 total atoms. If the oxygen is in the ring, that's a heterocycle. Maybe we take the oxygen out of the ring. So we have a 4-membered ring with just carbons. And so now we have to put the oxygen in, so that means that it has to become an alcohol. So the top one is an ether. The next one is an alcohol. You could even make a 3-membered carbon ring. So now you have a carbon and an oxygen to take care of. So I put them both on the same carbon of the ring, but you could move them around. And then again, sorry, from that, practice the unique carbon, unique hydrogen sets and the ratios. And that's going to help you differentiate them. You'll find that they should pretty much be different for every constitutional isomer you work through. So again, the point of this type of problem is practicing calculating degrees of unsaturation. What's the influence of the heteroatom? And then logically drawing these out so that you're drawing either if it does have a degree of unsaturation, a pi bond or a ring, and then what functional groups you can accommodate in there. So the new concept we'll introduce first is the formal charge. And this really comes into play when you're looking at an element and it does not obey the neutral bonding pattern. And so I've written them down here. Hydrogen, carbon, nitrogen, oxygen, halogen. The group number, so we're going to use that group number in this equation that's shown. In the neutral bonding pattern, hydrogen has 1, carbon 4, nitrogen 3, oxygen 2, halogen 1. And then when it's neutral, these are the electron pairs that you would draw with it. So the equation that I use, your book may use a slightly different one. You look at the element, find the group number, subtract the total number of unpaired electrons, and then furthermore subtract 1/2 of the bonding or shared electrons. So let's do it for something that's neutral so that you see it ends up being 0, and then we'll look at, in particular, these 2 nitrogens that are showing those charges. So right here for that carbon-oxygen double bond, the carbonyl, I've put in the lone pairs. And so if we calculate formal charge for that oxygen, oxygen is group 6, we're going to subtract off 4. So that's 4 total. I call these unpaired. That's really not the best descriptor, I guess. Maybe I'll say the total oxygens, or the total electrons in the lone pairs. So there's 2 lone pairs, but 4 total electrons. And then minus 1/2, we're showing 2 bonds, which is again 4 electrons. So we get 6 minus 4 minus 2, that gets us 0. And you can do that for every element on there that's not showing a charge. Let's do this first nitrogen that's showing negative. How does that end up being negative? So nitrogen's group 5. We're showing 4 electrons. So the total number of electrons in the lone pairs, that's 4. And then we have a highlight in red here. There's 1 bond, there's 2. So this number ends up being 4 as well. So we get 5 minus 4 minus 2. So that's 5 minus 6, it's negative 1. And then we'll do it for the nitrogen next door. Group 5. So notice that that nitrogen is showing 0 electrons in terms of the lone pairs. We have 1, 2, 3, 4. So that's 8. So 5 minus 4, that gets us plus 1. So really visually what you're trying to clue into, and there's a problem like this on the exam, is when you're looking at the elements, do they have the neutral bonding pattern? If they don't, then you'll have to go through this exercise. Any questions before we do problem? So the molecule shown is called nitrobenzene. The nitro group is another functional group that we'll learn a little bit later on. It's not terribly important to us right now, but it does have formal charges in it. And we have the blue nitrogen and the red oxygen. So we need to assign formal charges to those 2 atoms using that equation. So we know that nitrogen normally has 3 bonds and then 1 lone pair of electrons. As it's drawn, it's only showing, it is showing 4 bonds and no pair of electrons. Oxygen normally has 2 bonds, 2 lone pairs of electrons. So here it's showing 1 bond and 3 lone pairs. So eventually, once you see enough of these, you'll be able to just say, okay, this is plus, that's minus, and you don't necessarily have to go through this equation. So let's do the nitrogen. It's group 5. There's no lone pairs, so that's 0. And then minus, we have 1, 2, 3, 4. 4 bonds, so that's 8 total electrons. So the nitrogen should be plus 1. So from that, we can eliminate A and B. And then just using some chemical intuition and logic, the oxygen has to be negative. You know, just like there's conservation of energy, there's conservation of charge. So if you have a plus, it has to be balanced out by a minus. But let's calculate it anyway. Oxygen's group 6. We see 3 lone pairs of electrons, so that's 6 total. And then minus 1/2 of just that one bond, which is 2 electrons. So 6 minus 1 gets us -1, so that's negative. So we eliminate C, and then D is the correct answer. So 2 reasons I've shifted the exams to outside of class. One is students often have other obligations, so meeting in class for an exam tends to impact some people. The other thing I want you to think about is think of the number of steps you have to do for each problem. You know, you're applying these sort of questions as you go through it, and that's an algorithm. That takes a certain number of time. Students tend to get stressed out. If, you know, there's 30 questions, you have 60 minutes, so that's like 2 minutes per question. So stress is a big influence on performance. So if you have 24 hours to do this, find a nice quiet spot. You can go through your notes, your textbook. I'll caution you this, however, please do not set up a chat stream where you're just listing the key for other people. That's not in your best interest, because when it comes to the final exam, you're going to be sitting in this classroom for the final exam, and I'm going to be watching sort of the behavior a little bit more closely. You know, but again, do your best to do this to the best of your ability. And that's sort of all I'll say about that. Okay, so one more question about assigning formal charges, and this is something that we saw in general chemistry for an actual reaction. So water undergoes autoionization. That basically means you have a neutral molecule that splits apart and forms these 2 ions. So H and then OH, and then each of those species has a charge. Remember, the charges have to balance to give you ultimately 0. And so just off the top of your head, what charge should I assign the H? Plus, so we call that a proton. So it's no longer hydrogen because it's lost its electron, it's a proton. So if that's plus, then the other thing we call hydroxide. So that has to be minus. And in chemistry, things that end in IDE are typically anions. So this is a cation, it's positive. This is an anion, it's negative. So our answer for this would be D. So if we just go through the exercise, just for the oxygen here, it's group 6. There's 3 electron pairs, so that's 6 total electrons, minus 1/2 of the OH bond. So that gets you the -1 that we see on the oxygen. And so the hydrogen has to balance that out, so it's plus. So here is a summary of that in a table form. In the middle is the neutral bonding patterns. To the left is when those elements will have a negative charge. You can tell that by counting the number of bonds, the number of lone pairs. Then to the right is when those elements will have a plus charge. And again, you see the bonds and the lone pairs change. So for now, you should be comfortable with looking at a structure to see if it's in the neutral bonding pattern. If it doesn't look like that, then go to this equation to calculate the formal charge. So which of the following does not correctly assign the formal charge to the oxygen? So someone said the first one. That oxygen is showing 1, 2, 3 bonds. This third one is also showing it, so there's a discrepancy between the minus and the plus. The first one's incorrect. When oxygen has 3 bonds and 1 lone pair, it's plus. The second example is the neutral bonding pattern. The last example is when oxygen's negative. So it has 1 bond and 3 lone pairs, so it ends up being negative. So that first one is the one it's not correctly assigned. Any questions so far? We're going to circle back to that molecule AZT. We talked about the formal charges on the 2 nitrogens, but there's also another thing that we need to know as part of Module 1, and that's called resonance. So resonance should be familiar to you from general chemistry, but for organic, there's specific sort of rules that we want to consider. And we'll look at the nitrobenzene example, but then we'll also look at AZT again. Let me first say that this arrow in the middle, that's the resonance arrow. So this class will look at a lot of different types of arrows. the sort of double-headed arrow as shown, that's called resonance. And you have this structure here, which is called nitrobenzene. This other structure, which looks like the same thing, but it's kind of different in a way. Resonance is tricky because it's not two separate things. Resonance is just telling you, okay, these atoms in the molecule might have more charge or less charge than sort of as would be drawn with one structure. So let me draw something out here. I colored that oxygen red and gave it the negative charge. But then over here, I put that negative charge on the black oxygen. So again, these are not two separate things. They're one molecule that's basically telling you, okay, that negative charge can reside on either oxygen or both, where both is getting sort of 1/2 of the negative charge. Another type of arrow that we use to show that, the movement of those electrons, is called a curved arrow. So I'm starting at a lone pair on this red oxygen. I'm curving the arrow, and what it's telling you is that it's now going to form a double bond to that nitrogen. If we're forming a bond, we have to break an existing bond. So we draw another curved arrow from the pi bond to that black oxygen that then puts that third lone pair on the black oxygen. An important thing to recognize for resonance, and I say it down here, it's really only dealing with 2 or 3 atoms total at any one time. So we have oxygen, nitrogen, oxygen. You're not moving atoms around. You're either moving a negative charge, a positive charge, or an unpaired electron, which is called a radical. Yep. So that's a boo-boo. So again, the stuff on the slide I do in a program called ChemDraw. I just forgot to erase it. So just erase one of those as best you can. Maybe I'd white it out, but this won't let me do that. So resonance is the delocalization of electron density through a pi system. So in that nitro functional group, so I'll draw a little ball for the rest of the molecule. So you have 3 atoms, and there also has to be a pi bond. So you've seen a couple different types of pi bonds now, CC, CO, and this is an NO pi bond. So 3 atoms, a pi bond, and you're basically moving the electron density around. Electron density is a lone pair of electrons, an unpaired electron called a radical, a carbocation, or it can be a pi bond, as you see in this bottom example. So this molecule is called benzene. And really the difference between the two structures, if we're to push the arrows, you see that the pi bonds in the first one migrate to the alternate positions in the second one. And the reason that's important is because all of the carbon-carbon bond lengths in benzene are the same. We saw a couple lectures ago that as we draw a sigma bond, that is normally longer than a pi bond in an alkene. So the resonance makes all of these bonds, whether it's shown as a carbon-carbon sigma bond or a carbon-carbon pi bond, they're the same length. And that's due to resonance. So I said that resonance is not the movement of atoms. So what's shown in this reaction, notice how the arrow looks different. So that's not a resonance arrow. This particular example is called tautomerism, which is the movement of a hydrogen. If we're to count 1, 2, 3, we can see that hydrogen migrates from carbon 1 up to the oxygen at position 3. So again, that's not resonance. In resonance, the bonding pattern essentially has to stay the same. So this one, when you're moving a hydrogen, that has a different name. So again, a learning strategy that students use, you just go old school with the 3x5 flashcards. You write the vocabulary word on one side, and on the flip side, you draw the example.
Is that arrow only in order to keep the constant?
So this arrow we call it an equilibrium arrow because you have a forward direction and then a backward direction. So generally it's called equilibrium, and that can mean under that like various classes. So tautomerism is one. There's others that we'll learn. So here's the molecule AZT. And what I've drawn with already on the slide in the red curved arrows, I'm taking that negative charge on the nitrogen that's bonded to the ring, and I'm moving it down to the terminal nitrogen. Notice that the central nitrogen still stays plus, but now the terminal nitrogen is bearing the negative charge. So highlighted in red there, those are the three atoms. You have the pi system, and then we're showing the movement of the negative charge through resonance. So overall, what it's telling you is that nitrogens 1 and 3 are more negative. The central nitrogen is positive. Question?
Where's that thing, the red
I'll get to that in a second. So let me just write this here again. So the red arrow the curved arrow is showing the movement of electrons. So a way you can think about that using a sports ball analogy is, you know, the center hikes the football to the quarterback. The football is the pair of electrons. The quarterback is throwing it. That throw is the trajectory, and then it's caught by the receiver. So the red arrow is sort of the trajectory of how those electrons are moving. And as we learn more about mechanisms, there's rules to how the quarterback can throw the football to the receiver. And we use different chemistry terms to describe that. But again, that follows a set of rules. So what I've already written in red, it says amide resonance. And so when we look at AZT, I don't want to do that. So there's a carbonyl. It's bonded to a carbon and a nitrogen. So that's an amide. The nitrogen has a lone pair of electrons. So while the nitrogen looks like it's sp3 hybridized, in its sort of normal valence state, it's actually not due to resonance. So how do we explain that? So CNOF, we know that moving towards fluorine increases electronegativity. So oxygen's more electronegative than nitrogen. So what it's doing is hogging that lone pair of electrons. So that lone pair will be delocalized onto oxygen. And the squiggles are just the rest of the molecule. So when the oxygen gets the lone pair, it's no longer in the neutral bonding pattern. It looks different. It ends up being negative. And so the nitrogen's positive. So in that resonance hybrid, that's a little bit more important. So it has a greater weighting factor. And as a consequence of that, the nitrogen is sp2 hybridized. And the reason for that is so it can move those electrons up onto the oxygen. Because what's happening is you have to conserve that pi bond. And so to conserve it, the nitrogen needs that p orbital, the carbon still needs its p orbital, so you form the pi bond. So a couple more questions and then maybe some more constitutional isomers if we have time. So of A, B, C, and D, which one has an oxygen that is stabilized through resonance? So all the oxygens are negative charged, so that's your atom 1. Then you go out to atoms 2 and 3, And remember, part of having resonance is that in that 3-atom system, there has to be a pi bond. So just based on that, we can eliminate B. A and C both have pi bonds, but what's the issue? They're not within that 3-atom system, so D is the correct answer. So a resonance form of D moves the negative charge onto that atom number 3 of that system. So again, these pi bonds in A and C, they're too far away. Another example. Again, this one says not. So which one does not represent resonance hybrids? So if you look at A, we're just migrating the pi bonds around. So that one's good. B. If you look at that highlighted hydrogen, it's actually moving from atoms 1 to 5. So again, resonance is not the movement of an atom. So B is going to be the correct answer for not representing resonance. C is resonance, because we're just pushing an electron pair from oxygen to form an alkene, or to form a double bond. So we're keeping all the atoms in their same places. We're just moving a lone pair down, and the plus charge goes from carbon to oxygen. So that doesn't fit in with the 3-atom system. It's 2 atoms of a carbonyl. And then finally, D, it's the 1, 2, 3. The plus charge is migrating from carbon 1 to carbon 3, and we would push the arrow like that. And so all the carbon atoms have to be sp2 hybridized. So we're about out of time, but here is another thing that you can practice on that molecular formula. Now you have 1 nitrogen, 2 oxygens. Remember, nitrogen will subtract from the hydrogen count, so you'll end up with C4H8. But now since you have a nitrogen, you can make other functional groups. For example, amines, imines, amides. Make sure you review those functional groups as well. So remember, quiz and exam, they're both open now, due tomorrow at 12.